Okay, now, as we saw, we stretched a rubber band out from here to here, and we determined the x and y components of the displacement vector from here to here. We then determined the angle of that vector, and we multiplied that by the force exerted by that rubber band when its length was equal to this distance being equal to the magnitude of that displacement vector. Then we stretched another thinner rubber band out. It got longer, but it was a thinner rubber band, so it actually exerted less force. And we did something very similar, or we're going to do something very similar with that rubber band. Now, summarizing what we did here, and I'm going to use R12 as the displacement vector. So our displacement vector here would be R12, and our displacement vector here would be R13. Now, for the R12 vector, which had components 9 and 10 centimeters, we in a very straightforward manner determined angle theta, which I'll call theta 12, to be 48 degrees, taking the arctangent. And the magnitude of F12, using the Pythagorean theorem, turned out to be about 13.5 centimeters. The magnitude of F12 based on the magnitude R12, 13.5 centimeters, determined by the Pythagorean theorem from the R12 vector, turned out to be 12 newtons, and we talked about how that happened. We just hung weights, and various weights used the trend to determine how much force would be exerted by that rubber band when it was stretched out to 13.5 centimeters. Okay, and we then determined that the components of F12 were 8 newtons and 8.5 newtons, x and y components, because the F12 force was in the same direction as the vector, and we had the 48 degrees. I also mentioned we could have bypassed the calculation of the angle using unit vectors. We'll talk about that before we're done. Okay, now we're going to do the same thing with this information then. Okay, our R13 vector is negative 9.5 centimeters, 13.5 centimeters. I just measured those, but if we had the coordinates x1, y1, and x3, y3, we would just subtract coordinates in the usual manner to get the components of this R13 vector. And I just realized I've got some color issues here, so I'm going to change something. Okay, I used green colors previously for calculations of R12, and I've circled this R12 now in green, and I'm going to use yellow to do the calculations for R13, and then I'll use blue to do the calculations for F13, so things match up. I don't use colors, I don't use any consistent color coding, but I try to maintain some consistency on a given set of calculations. Okay, so our R13 vector is negative 9.5 centimeters, 13.5 centimeters. And I want to just automatically, you kind of almost automatically do this anytime you see the components of a vector. You go ahead and calculate its angle and magnitude. Now, there are times when you're going to skip that, times when it's not necessary, but for right now, it just should be a knee-jerk reaction. So we calculate the magnitude of this, we calculate the angle, and you should go ahead and do that. So we get theta 13 being the arctangent of the y over the x component, and adding 180 degrees because the x component is negative. We get negative 55 degrees just from the arctangent. We add 180 degrees, we get 125 degrees, which makes perfect sense for a vector in this direction. From here out to here, we go up to 90, and a little more, we go to 125. Okay. And we get the magnitude just using the Pythagorean theorems, adding the squares, taking the square root, and we find that the magnitude is 16.5 centimeters, meaning that the rubber band was stretched out to a length of 16.5 centimeters. Then, based on measurements of the force versus the weight, or the length and the weight that the rubber band holds, we determine that that force has magnitude 7.5 newtons. Remember, this was 12. This is 7.5. That's about right. out to the scale that I drew here. And that's based on the fact that the magnitude of R13 is 16.5 centimeters. That would be the force exerted by that rubber band when it's 16.5 centimeters long. Okay, so now we have this force, and incidentally I rewrote this in the color that matches the color of the label of the vector. And I've done something similar over here. And you know, I'm looking at that board. I'm not sure everything shows. Let me move a couple of things here. Just wanted to be sure this labeling here and this labeling up here were visible, and I'm not sure they were. This is X3, Y3, this is R13, circled in yellow, and so forth. Should be clear how all that feeds into this. Okay, so now we have the force F13, and what do we need to do in order to figure out what these two forces, what these two force vectors would add up to? Well, what we need to do is we need to calculate the X and Y components of this F13. Okay, so its angle is 125 degrees, just as the angle is for R13, so we're easily going to be able to calculate F13X and F13Y. You should do that. Okay, calculation is straightforward. We just multiply the magnitude by the cosine of the angle. We get the X component. Does this make sense? Negative 4.3 newtons. Yeah, if we go in the X direction, we go over here, negative 4.3 newtons. If this is 7.5 newtons, it's very plausible if this is 4.3 newtons and it's in the negative X direction. And that Y is 6.1 newtons. It's very plausible. If this is 7.5, then this is 6.1. Okay? Now, we put all this together. So you should go ahead and see if you can't add the force vector here to the force vector here. Well, the addition is very straightforward. We have this vector, which can be written 8.0 newtons, 8.9 newtons, and the F13 vector, which can be written negative 4.3 newtons, 6.1 newtons, and we know that we can add the X components of the vector and the Y components of the vector, and this is what we're going to get. Now, what are the magnitude and angle of this vector? Okay, so we calculate the magnitude and the angle. Magnitude by the Pythagorean theorem, 15 squared is 225, 4 squared would be 16, 3.7 squared probably closer to 15. Add that to 225, you get 240. 16 squared is 256, 240 is somewhat closer to 15 squared than it is to 16 squared. Not really linear there, but I'm going to estimate that that's 15.4 newtons. And down here, the arc tangent of 15 newtons over 3.7 newtons. And to get that accurate, I use machinery. I can't estimate that to the nearest degree. I can get close, but especially when you get up into the angles near 90 degrees, it gets more difficult. So I calculated that, and that's 76 degrees. You can check my estimate on this one. Now we can depict a vector of this magnitude at this angle on the graph. 76 degrees is where? Pretty close to 90 degrees. It's going to be out about here. 15.4 newtons is somewhat bigger than 12 newtons. So I'm thinking the vector ought to be out about here someplace. So here's our total force. Total force from these two rubber bands. Now, I didn't draw that perfectly. I didn't try to, but I could have. Of course, I couldn't have drawn anything perfectly, but I could have done a little better job because, as it turns out, because of the way the components add up and so forth, I'm going to draw a bigger picture and go over this a little bit more. But if I draw a parallelogram, a line here, or dotted line, let's say, parallel to this, and then a dotted line from the tip of this vector parallel to this one, that's actually going to give me the ideal vector. And of course, this vector is I drew it somewhat too short because it's not a whole lot longer than this. I'm not even sure it's longer. This is supposed to be 15 point something, and this is only 12. That's not 15 point something according to this scale. Didn't draw the parallels perfectly. This one should have been just a little up here. But I'm going to correct parts of that figure. Okay, that's a little better, but it's still not exactly right. This goes a little bit beyond the corner of this parallelogram, but then this segment should be, or this dotted line should be angled out this way just a little more. And I'm going to leave the imperfections there. You get the idea that if I draw a parallelogram representing with a parallelogram, two of whose sides represent these vectors, then the total vector, the sum of the vector, the resultant of the two vectors will be from the initial point to the opposite corner of that parallelogram. Now, what does this mean? This means that if I stretch my first rubber band out, and I can't seem to find my first rubber band, but imagine that I'm stretching that yellow rubber band, the first one out from here to here, and the second one from here to here, then those two rubber bands together are going to exert a force that's not quite vertical. It's up at the angle 76 degrees above the axis. And if this force is 12 newtons, and this force is 7.5 newtons, that force is going to have a magnitude of 15.4 newtons, approximately, give or take a tenth, because of the round off and the approximations. And we could test that, actually. We could take a third rubber band, okay, and we could oppose these two rubber bands with that third one and see if the vector that we get for that one is equal and opposite to this one. Now, that's going a little deeper into the physics than we really need to at this point. We're just trying to get an idea of vectors and why we need to add vectors and why we need to use vectors to resolve forces in this case.